Well, thank you for your welcome. When we've got the computers all sorted out, that wasn't my computer that did that. So what we're doing today is we're looking at just a select part of the God Delusion because it's a fairly large book, and I'm looking mainly at chapter 4, and I'm looking at a scientific response to what Professor Dawkins says in chapter 4. If you're interested in more the theological side of things, there's a number of books out. One I've got here is the Dawkins Delusion by Alistair McGrath, who actually is I believe he's a professor in the same university as Professor Dawkins, who's written a more theological response to some of Dawkins' arguments. So if you're interested in that, we have a bookstall here actually for books, if you want to buy some books that discuss the creation-evolution debate. They're all written from a Christian point of view, defending creation as opposed to evolution, which is my position. But this evening's topic is looking at the scientific evidence that Professor Dawkins puts forward to suggest that there is probably not a God, and why I, after reading that, still maintain my position that there is a God. But we'll get to that later. I want to start off with a quote. And the next time somebody tells you that something is true, why not say to them, what kind of evidence is there for that? And if they can't give you a good answer, I hope you'll think very carefully before you believe a word they say. Anybody want to hazard a guess who said that? Richard Dawkins said that. He wrote that in an open letter to his daughter to encourage her to question the things people say. And I think that's a very good thing. We ought to do that. We ought to listen to Professor Dawkins, and we ought to say, okay, what is the evidence? And let's look at the evidence. And that's what we're going to do tonight. We're going to look at the evidence, and we're going to see whether it actually supports Professor Dawkins' thesis, or whether, after looking at the evidence, we can still have reason to believe that there might be a creator God. So I'm going to look at four main areas. We're going to look at natural selection, because Professor Dawkins claims that natural selection explains why we're here. We're going to look at something he calls the worship of the gaps. He claims that creationists worship the gaps and put God in the gaps. There's actually a misunderstanding of our position. We're going to look at the origin of life and the variety of life, because this is a very important issue when we're thinking about origins, when we're thinking about creation, evolution. Where did we come from? What is the origin of life? And how can does natural selection explain that variety of life? And we're going to finish off by looking at science and faith, because Professor Dawkins has some very interesting things to say about what faith does to science. And we're going to look at the evidence there too. So let's look at natural selection with some more quotes from Professor Dawkins' book, The God Delusion. He claims that Darwinian natural selection is the only known solution to the riddle of where the information comes from, the information contained in living systems. We all have a genetic code, and that genetic code contains information. Where does the information come from? Well, Dawkins says that Darwinian natural selection is the only known solution to that riddle. He also says that slowly increasing complexity explains the illusion of design. Biologists often talk about design, they do it all the time, and they often get misunderstood because some people think that if they're talking about design, there must be a designer. Well, when I talk about design, I do mean there must be a designer. But Professor Dawkins suggests to us that slowly increasing complexity actually explains this illusion of design. And he claims, in fact, that natural selection is a better alternative than the God alternative. So let's look at natural selection. Let's just look at a couple of examples of natural selection, and let's see what natural selection can do for us. Well, of course, we'd all probably heard about Darwin's finches. On the islands of the Galapagos, off the coast of South America and the Pacific, there are 14 species, or give or take. Maybe there are 12, maybe there are 15. It's a bit unclear. But there are about 14 species of finch. And here are the pictures of some of them. And they differ mainly in beak size and shape. So the distinguishing features of these different species are the beaks. You look at the beak and you can identify different species. And this is mainly associated with the different types of food that they eat. There are other differences as well, but we're going to just look at the beak and the diet that these finches use to survive and what that teaches us about natural selection. Here we have one of the finches with a very large beak, Geospitzer magnirostris. There's no why I didn't do Latin. And then we have G. scandens, And you can see the beak sizes are different. We've got on the left-hand side a bird with a very deep beak, and on the right-hand side a bird with a narrow beak. And this is associated to the type of food they eat. And the bigger, stronger beak you have, the larger, harder seeds you can eat. And there's quite a lot of research that has been done on these finches by a couple, the Grant couple, Mr. and Mrs. Grant, who've lived on the island, have worked for 20 years or more studying these finches. And there's lots of different evidence that shows how the size of the beak determines the size of the seeds there. Here's a graph. You've got 3 finches here, smallest beak on the left and the largest beak on the right. And the larger the beak, the larger the seeds. So the bird on the right-hand side there eats seeds that are about 5 to 7 millimeters in diameter, and they can crunch those up and survive quite happily on them. But what happens in terms of natural selection is that as things change on the island, the size of the beaks change. And here we have some very interesting work which is affected. We find that the beak is actually affected by the weather. Well, not directly by the weather, because the weather affects the amount of seeds that are available, the type of seed that's available. So in dry weather, you tend to have less seeds, which are harder, more shriveled up, more difficult to eat. So the birds tend to have larger beaks, because the larger your beak, the more force you can apply, and the more easily you can obtain food. Whereas if you've got a small beak, you tend to do very badly in these kind of conditions because the food is too difficult to eat. So you tend to die out. So what you find is, as you measure the beak depth over the years, starting from 1979 up until 1982, there are some blips. Every time there's a very dry year, the seeds type that's available is very hard and dry. So the beak size of the finches, you find, has increased because the ones with the small beaks can't eat, so they die. So here we have natural selection in operation. Basically, the food is the environment that changes as a response to the weather, and the weather can have a big effect on the type of bird you find. Well, big effect. Actually, we're only talking about a few millimeters in beak size, but it is a difference. And then when there's wet weather, more seeds are available, which are much easier to eat, and you get the birds with the smaller beaks coming back. So you can measure the beak size, and this is exactly what happened in 1984. Wetter weather, the beak size decreased because there's much more available food, and the type of seeds that are available were much easier for the birds with small beaks to eat. So here we have natural selection. We have the survival of the fittest. Those birds which are best adapted to survive in the harsh conditions survive. Those which are not able to obtain food, they of course die and don't leave many offspring. So you have a variation in beak size responding to that environmental condition, and that's observable biological effect. That's natural selection, and I have no problem with natural selection. Natural selection is an observable thing. You can measure it, you can quantify its effects, just as has been done here, and this is nothing to challenge anybody's faith. I'm perfectly happy with the idea of natural selection, and it's not going to cause me any problems. So there are many things where I can agree with Dawkins, and I agree that natural selection is a very important phenomenon in biology, and it's very important in understanding biology and how biology operates. Let's just look briefly, though, at genetic variations and how that fits in with the story. Again, picking one of the very well-known examples of evolution, the peppered moth and a phenomenon called industrial melanism. You may well know the story. The peppered moth is a moth which is got a basically mottled pattern, and you have here in this picture actually 2 moths, one of which is rather more easy to see than the other. There are 2 varieties of peppered moth. One is the dark form, one is the lighter form, and in case you're having trouble, the lighter form one is here in the green circle. You can probably see it now. And what happens is, the story goes, with pollution during the Industrial Revolution, the pollution killed the lichen on the trees, turned the tree trunks black, and so these light-coloured moths were much easier to see, and the dark moths replaced the light form. And here we have evolution in action. Here we have actually a change in gene frequency, because the gene for the dark form became more common than the gene for the light form, except it probably isn't just one gene, it's probably a bit more complicated than that. But it's an example of evolution in action, or at least it's believed to be an example of evolution in action. And here we have pictures which show you the 2 different forms on 2 different backgrounds. On the left-hand side, you have the normal tree with the lichen, which is light-coloured, and the light-coloured moth blends in very well with that lichen and is not visible. And on the right-hand side, you have the darkened, soot-covered tree trunk, and of course the light-coloured form is much more visible. And if you're a bird looking for a lunch, you're going to spot the light-coloured moth on the dark background, and you're going to eat it, so the dark one survives and the light one disappears. And there's a selection for the dark form over the light form, so you get a change in distribution, you get a change in frequency of the two different forms, which can be interpreted as a change in gene frequency driven by natural selection. But there's actually a bit more to the story than that. There's been a bit of controversy about the peppered moth, and there's been some evidence that's come forward suggesting that the results that were initially published back in the 1950s were not as well founded as was believed. And recently there's been a swing back in the other direction, but we're going to look at that briefly. But here's some problems for the peppered moth story, which shows it's a little bit more complicated than sometimes presented. Here we have a chart of Great Britain prepared in 1971, where you have the distribution of the different forms of moth. We have circles here. If you have an open circle, that means 100% of the moths are the light form. If you have a closed black circle, that means 100% are the darker form. And then you've got a pie chart effect, where you've got more or less the lighter area. That's basically showing you the distribution, proportion of the two forms in different parts of the country. And it works very nicely for Liverpool, where you've got pollution. The dark forms are the predominant form. But then you've got the distribution is actually rather strange, because you can find in some areas where there's no pollution, 80% of the moths are the dark form. So why are they there? Surely they'd all been eaten by the birds, so there'd be much less than 80%. So this is the first problem with the story. The light form persists even in polluted areas. But as I say, there's been some research done, and there's actually some work published in August 2007 by a gentleman called Magirus. I don't know how he pronounces his name, that's how I pronounce it. He's based in Cambridge University, and he was interested in this story, and he published some material that actually caused a lot of people to question the story and say, well, this is not actually good evidence for evolution as we believed. And he said, well, I didn't really want to do that. I wanted to show that it was quite good evidence. So he's been repeating some experiments, and he spent 6 years between 2001 and 2006 doing capture and release experiments near Cambridge with the light and the dark form of the moth. And what he found was, actually, the story seems to be confirmed in that the more dark forms are eaten than the light forms, because contrary to what was said before, at one time there was some evidence suggesting that the moth didn't actually land on the tree trunks at all, so it wasn't actually visible to any birds, so they couldn't eat them, whereas in fact he's found that they do tend to land on the trunk as well as on the branches. So as far as that part of the story is concerned, it seems to be confirmed. So, and predation, in other words, being eaten by a bird, is a major cause of the decline of the dark form, because now in Cambridgeshire what's actually happening is the dark form is becoming less common and the light form is more common, rather than the original event, which was the pollution which caused the dark form to become common. So we seem to have a mechanism to explain natural selection in action causing a change in gene frequency. But it's not quite so simple, because the dark form still persists. So whatever happens, in most areas you still find dark moths. But overall, there is definitely a change in gene frequency, and natural selection does seem to be one of the factors that is driving this. So we have to conclude, yes, natural selection is doing something. Natural selection is a real effect that we can measure and we can understand. And natural selection does do something. Natural selection eliminates the unfit. If you're not fit to survive, you get eliminated in a natural world. When we talk about human beings, of course, we protect our weaker members so they don't get wiped out. But if you're a moth living on a tree, it's nature red in tooth and claw. Natural selection will eliminate the unfit. Only the strongest and the best adapted will survive, and we have no problem with that. But random mutations reduce fitness generally. Not always, but generally. And of course, natural selection, eliminating the unfit, will tend to stop changes. And the one thing about natural selection that's never actually been demonstrated, and this still stands, is natural selection has never been observed to produce new features. And we're going to come back to this later at the end. But what we can say positively about natural selection is natural selection can cause changes in gene frequency, and the peppered moth is probably quite a good example of that. Natural selection does cause survival of the fittest. That's a well-established concept that can be demonstrated with the evidence. And it probably causes speciation. And one species can be split off into two different species and diverge slightly in appearance.